All right, everyone, let's get started here. This will be our last lecture of the semester, and then we have a final which takes place next Thursday. Are y'all happy about that?
Yes, actually
it's Thursday, right? It is Thursday, yeah. It's Thursday at 12:30.
Professor's excited because then after that they need to practice this.
I wish it was Tuesday, then I would not have a final on Thursday, but...
He's like, don't worry, I've already started that model. My whiskey drinking starts on Wednesday.
Wait, I didn't hear the whiskey drinking part. Okay, so look, let's get some stuff out of the way. I have everything that I've graded is sitting up there in the corner, right? Make sure you grab that. And then the SLO assessment, sorry, you don't know what I'm talking about. The quiz I gave you last time with the farmer and his fence thing, I just wanted to give that back to you just so you could look at it real quick. These were the correct answers. And really, this is not the correct answer for 7, but that's the correct answer I wanted. You're supposed to give the dimensions of the pen, but if you need that first before you can answer the question. So if you got to that, I gave you full 100%. And so on your grades, that grade is the last quiz, whatever that is, 8 or 9, I can't remember. Yes?
I was just wondering, like, seeing, I didn't know you did.
Yeah. Anyone else need theirs? Did I bring the right class?
Yeah. There it is right there.
Okay. Here, take that. You can just put it back on that corner. I need those back, though. Okay? I have to have those back. So when you're done with it, just put it back up on the or back up on the desk. Y'all did pretty well on it. I think y'all did better than my other class, but
Yeah, sorry.
that was good. I was happy to see that. All right, y'all ready?
Oh yeah, I agree. Like trying to, I ended up just like trying to do it on my own and then go back and trying to pick it out.
Okay, so I sent out an email. Did I do that on Tuesday? Did I tell y'all about it Tuesday? Okay.
Sent an email, something like, it was like some sort of.
Yeah, okay, so I sent you 2 emails. One of them had the kind of an old version of a final, right? And I said in that email, make sure you do study your homework and everything else. And then later on, I sent another email that had a list of problems from each of the, I took them from like mostly the chapter reviews. And
It was a special when I received it.
no. And so that's another thing that you can study and just kind of narrow your focus on. And then I've got one additional thing here for you. For the final, of course it's going to be Thursday, next Thursday, at 12:30. That's kind of the important thing because our class normally starts at 1, but it's at 12:30 and it goes till, what is it? 3 hours? Almost 3 hours? All right. 2 hours and 45 minutes. I think it goes to what, 3:15 or something? 3:15. So I don't know if it'll take you that amount of time or not. It depends on you, of course. But that's the amount of time that we have for it.
I know you said you hadn't made the final yet, but.
Yeah, I'm about to talk about that. So here's what I told my other class. I'm going to pick problems from chapter 1, and I'm going to tell you the things that I think will be there or won't be there. You know, kind of narrow things a little more for you. For chapter 1, the main idea here is that's limits, okay? And so you need to be able to do some of the limits by hand, and that means I'm going to have to give you some that L'Hopital's rule doesn't really work real well with. Okay, so that doesn't mean they're harder, it's just that this is the ones where you had to come in with the conjugate or something like that, and do the conjugate on top and bottom, and things worked out. This is going to make up about 10% of your grade for the final, the material from chapter 1. And then in chapter 2, this is derivatives. And there's a lot of stuff that could be there from chapter 2, but specifically, you need to remember how to take the derivative of a function using the limit definition. That was the limit as h goes to 0 of f of x plus h minus f of x over h. The old school way before we got the shortcuts. I'll ask you to do a limit like that. I'll say use the definition, and then you do your work, and you can always check your answer by using the shortcut rules, right? Yeah, you should get the same answer both ways, right? So be prepared to do that. Be prepared to find the equation of a tangent line. So that involves, you're going to need a point, and you're going to need the slope of the tangent line. The slope of the tangent line comes from, where's the slope? It's the derivative, right? So you're gonna need to be able to do that. And then, the rest of that chapter is, there's a lot there. Product rule, quotient rule, chain rule, implicit differentiation. Okay, but the problems I gave you in that email will kind of like help you focus on those ideas. That's also going to be 10%. And then chapter 3, which is inverse trig functions, exponential, logarithmic. This is where you're doing like logarithmic differentiation. Make sure you know how to do logarithmic differentiation. And that's where you would, like for example, taking the derivative of x to the x. When x appears both in the exponent and the base, you have to come in with log on both sides and take your derivative. So logarithmic differentiation. Also in that section is L'Hopital's rule. Or in that chapter, I should say, is L'Hopital's rule. So be able to do L'Hopital's rule. This section is going to be 20%. Or material from there. Now chapter 4 is where we get into applications. And so I will give you a function on a closed interval, and I'll ask you to find its global max and min. So that's the closed interval method. Be ready to do that. I'll keep the function clean. It's not going to be some crazy function. What I'm trying to do in this test, just so you understand, is I just want to be able to go back, kind of give you kind of not, I don't want to say easier problems, but just foundational problems that show that you understand the concepts for each of these main topics. So the closed interval method is probably going to be a polynomial. It's going to be easy to take the derivative. It's going to be easy to set it equal to 0. It's going to be easy to find your critical numbers. So it's not going to be some weird thing with roots and product rule where you're going to have to try and, you know what I'm saying or not? Okay, so as long as you understand the concept, you'll be okay. I will not ask you to sketch a function, okay, that big old long process. What I will ask is that you show where a function's increasing and decreasing, concave up, concave down, local max, local min. So it's, you take the first derivative, set it equal to 0, figure out where it's undefined, draw your little number line up, down, and then the same thing with the second derivative. Yeah, so concave up, concave down, inflection points. Again, a nice little polynomial. So it's, again, not trying to trip you up on the derivative part of it, just making sure you understand the method. All right? Trying to remember. Oh, optimization. Somehow I passed up related rates. Oops, chapter 2, related rates. Something very basic on a related rate. Circles growing so that its area is increasing at blah, blah, blah. So go back and look at that related rate section. I'm back in chapter 2 because I forgot. I'm not going to give you something like, the person walks away from the light pole and, I'm not going to give you something complicated. Very basic geometric shape. Again, just showing me you understand how to differentiate something with respect to time, how to write down what you're given, what you want, right? All that stuff. Okay. Back to chapter 4. Optimization. You just did one of those with the farmer problem. I have not decided for sure if I'm putting one of those on there. But if you could handle the farmer problem, the one that we just did, something similar to that, I think you'll be okay. I'm not going to give you anything crazy like try to find like a cylinder and a sphere type thing. I'm not going to give you anything like that. And then chapter 5 is antiderivatives. Well, actually 4.7, the last section of chapter 4, and then chapter 5 is antiderivatives, this integration idea. That's going to be in there also. And I haven't decided how I'm going to break this all up. All I can tell you is that I know that that's going to be the remainder of the test. So what is that? Can't do simple math. 60% here. So I want to keep things kind of heavier on this final with material that comes from the last 2 chapters. Applications of derivatives, max-min stuff, and antiderivatives. I hope that helps. My other class said the same thing. Yeah, let me put on here bonus. I can think of something. Sure, I can think of something. All right, so I think that's about all I can tell you about the final. I don't know how many questions it is. I have not made the final, so I told my other class my initial kind of guess as to how many problems, 20-ish, 20? No way it's going to be over 30, and no way it's going to be under 12. It's going to be somewhere between 15 to 20 problems, give or take. All right. What I normally do not do is just like take last semester's final and just like redo it. Every time I do a test, it's always just I decide for that class what it's going to be. So, all right. I hope that helps. All right. What else are we going to do today? That's it? We're done? No, we're going to do the evaluation theorem. And we're also going to do another substitution, because I just want to see, did anyone get an opportunity to work on the substitution at all? Or it's okay if you haven't, I'm just curious. No?
Is there a way, can you send out an answer key to those problems that you sent us?
I like the way you're shaking your head. Oh my goodness.
He's like yes.
Maybe. Maybe. Yeah, I can maybe. It just depends. I got to look at my weekend. Yeah, I'd rather do a video. It's easier, not easier, but it's something I can do once and not have to do again. Maybe, we'll see.
Why are we doing an answer key?
Well, I don't mean it like that way. I mean it as if I'm going to work the problems out, I may as well do it in a way that I can communicate what I'm doing, as opposed to just putting it on a piece of paper where you have to figure out what I did. So that's what I mean. It's more useful, I think, if I do a video. No promises, Laura. I'll do my best. Yeah. All right, so let's do a substitution, all right? Let's do another substitution problem. And I'm just going to write this one down. I guess we could start off with something easier, but this is right out of the book. Sine 2t over 1 plus cosine squared t. I said t, right? And then I wrote x, sorry. They use t as a variable here instead of x. Now, here's the good news, all right? And this is also the same is going to be in effect when you actually take Cal 2. Is while you're doing your homework problems, you know what section you're in, and so you know what the technique is to go after this. This problem comes from this substitution section. So we know that there must be some sort of substitution I can make here to be able to solve this. It's just coming up with it. So the key was to try and find something, to see something and its derivative, right? And the derivative, it's okay to be off by a constant. And that derivative, when I identify it, it should be in the numerator. It should not be in the denominator. It should not be trapped under a root or anything like that. So free from everything else. So do you see something in its derivative? Or do you see...
Maybe use the double angle.
Okay, so you noticed, Laura, that sine 2t and cosine t are different, right? A 2 inside there with the t is different than the t in here. So if you were to just right now say, hey, I think cosine t is my u. Let's just say you did that. The derivative of cosine t would be negative sine t, right? And this is not negative sine t, that's sine 2t. So it's not the same, right? So Laura's saying, well, wait a minute, I know from pre-cal that I could rewrite that, right? Using the formula for it. And what is sine 2t according to the formula?
2 sine t cosine.
2 sine t cosine t. 2 sine t cosine t over 1 plus cosine squared t dt. Do y'all agree with that? Yeah, okay. So now at least all my trig functions have the same, what's that thing inside the trig function called? The argument of the function. Okay, the thing that's inside of a function is called its argument. So they all have the same argument. See here, they didn't have the same argument. This was 2, this was, this was t, this was 2t. So now at least they have the same argument inside. Do you see something in its derivative? If you see it, don't tell me. Just if you think you have it, raise your hand. Okay, you think you got it? So we got one person so far. What do you think you've got something there? Okay.
I mean, we have to do one more step.
Okay. Think so? All right, for those of you who are not sure, do you have any like educated guess as to what it might be?
You have to factor the bottom to get regular cosine instead of cosine squared.
What do you mean factor?
Like, oh no, it's a sum.
Yeah, it's a plus. You can't. Sine. Okay, so I think, look, let's just look at this for a second. If u was sine t, right? And this is what you have to do when you're in this class. You have to actually try something. And it may not work, and then you just tear it up, throw it away, and you start a new piece of paper and you do it again. All right? You have to be prepared to fail more than you succeed in this integration. So let's just try this. If I write sine t, the derivative of this with respect to t would be cosine t, right? So do you see cosine t somewhere? Yes. It's right there, right? And right here. Now this is a problem. But why is that a problem? I said that the derivative should not appear in the denominator, right? And it's in the denominator. That's not usually a good thing.
Can we use logarithmic differentiation?
You're not trying to take a derivative, though.
Well, I mean, can you use the property of logs backwards?
No. So you see, this is maybe not going to work. So what about cosine? What if you let u be cosine t? Let's just see what would happen. We switch it. If this was cosine t, then this would be negative sine t, wouldn't it? Right? If we let u be cosine t, that's negative sine t. And so we have a sine t here, don't we? Now, we have negative here. We're off by a sign. And I said that's okay. And that derivative, it appears up here, doesn't it? Do y'all follow that? That looks promising. It looks really promising.
When you say find something and its derivative,
Yeah, so you're looking at this and you're saying, do I see anything in here that if I call that my u, I also see its derivative in there.
You're just testing different parts until you see its derivative also.
Yeah, you're looking in there trying to find something and then a separate piece that would be the derivative of that something.
Only in the numerator, if it's a fraction.
The derivative can only be in the numerator. So does this look somewhat like we might be on the right track? Yes, maybe? Okay. Now, Laura, is that what you had picked? No?
Was gonna do, I messed with that.
No, don't mess. You may not have messed it up because this is not what I would pick. So this is not quite. Okay. Did you have something different?
Well, I don't think it would work because it's stuck with that plus. But did I do secant squared cosine? Because it's 1 over cosine. But
Well, it's plus, yeah. So you couldn't do that. Okay. So was 1 plus cosine or 1 plus cosine squared? Can't quite do that because you would have to pull the squared. Do y'all see it? You couldn't say 1 plus cosine because how would you rewrite this? Like if I call this u 1 plus cosine t, then what is this then? This is not 1 plus, this is not u, right? This is not u squared either.
This cosine written twice.
Yeah, so the only thing you could do is pull the square. Uh-oh, is that going to be a problem? I don't know. What's the derivative of that? What's the derivative of 1? What's the derivative of cosine squared t?
So
2 pops out.
sine.
Cosine to the first power, right? Times the derivative of what's down here. Negative sine t, right?
Hold on. There you go.
That's chain. That is it, right? We're off by a little bit. I have a 2, a cosine t, and a sine t. A 2, a cosine t, and a sine t. And I'm just off by a negative, and that's okay to be off by a negative. Y'all see it now? Do you see why I'm saying that in Cal 2, you've got to be good at Cal 1? Like you've got to see these derivatives in order to be able to go backwards. You've got to see this. Yes?
So, in other words, the something can't be in the denominator as long as its derivative is in the numerator.
That's right.
Okay.
The something that you're first trying to identify can be anywhere.
Okay.
But its derivative needs to live up on top. And you're going to see why it needs to live up on top as I just proceed through this. Was there something else?
How do you get 2 sine t cosine t?
This is a pre-cal formula. It's a double angle identity. Yeah, so this is kind of, the reason I like this problem because in order to start it, you've got to at least know that part. So, and so now you start going, wow, any of these formulas from pre-cal are like on the table now. Yeah. And they're on the formula sheet, yes. There's also another way you could go. Well, no, never mind. We won't even go there. All right, so are y'all with me on this? I'm going to rewrite this now. I'm going to write du is equal to negative 2. I'll write it another way. Sine t cosine t dt. So all I did was brought the negative out front. I switched the order of the sine and cosine to make it look like that. And then remember I said this du dt, I'm always going to multiply both sides by the differential, the thing on the bottom, right? In our other problems it was dx and we just did that on both sides. So this is where I stand. Was that a question? Yeah, what do you got?
Did you have put sine squared t on the denominator?
Sine squared t, what?
1 plus cosine squared. Isn't that sine squared?
1 minus cosine squared.
Oh,
Yeah. Yeah, if that was 1 minus cosine squared t, this probably would have worked a lot different. Well, actually, no, it wouldn't. We could make the same substitution. But it may have simplified before we even did that. All right, so now what I'll do to try and help illustrate what this is going to turn into is I'm going to rewrite it. Okay, I'm not doing any integration yet. I'm going to rewrite that as, and just let me write it and then we can talk about it. This is this, isn't it? I just slid that numerator off to the side, and so that it joined up with the dt. Do you see why now that derivative part has to live in the numerator? Because you have to be able to slide it out like that if you're going to get it to match up. If it's down here, you can't pop it out like that. Make sense? So now I play my little matching game. I know that everywhere I see 1 plus cosine squared t, I'm going to replace that with u, right? So this denominator part is going to be replaced with u. So that's going to turn into 1 over u, right? And I start thinking, can I integrate 1 over u? I start running through my formulas. Antiderivative of 1 over x is natural log of x, right? So the antiderivative of 1 over u should be natural log of u. So I'm feeling good. I'm going to be able to integrate this. But I also need to match up the next part, which is the sine t cosine t dt. I see that, and the 2. Sorry, forgot to grab the 2. That right there is this, right? All of that's going to be replaced with, well, du, but the negative is a problem. So I can very easily remedy that situation by multiplying both sides by -1. And this becomes negative du equals 2 sine t cosine t dt. And now it looks exactly right. And so now I can rewrite the integral. Okay? So this integral becomes, this transforms into a new integral. It is 1 over u times, now what's this? Negative du, and it's not minus du, it's times negative du. So this is really like negative du, like that. And I'm gonna do one more thing before I actually finish this. I'm going to pull a negative out, because that negative is really like a -1, isn't it? I can pull a negative out. The reason why I'm allowed to pull that out is because we talked about this. When you have a constant in front of a function, when we took derivatives, the constant came for the ride. When you integrate, the same thing happens. If you have a constant out front, it will come along for the ride. So this -1 is just going to be multiplied through whatever my answer is. So this right here, antiderivative of 1 over u, ln of absolute value of u. So I have -1s coming for the ride, times natural log of the absolute value of u. And I also always have to put in there plus c. And I'm almost done. I just need to replace u. So what was u? 1 plus cosine squared t. So negative natural log absolute value 1 plus cosine squared t plus c. And I technically would not need the absolute values sign, because 1 plus cosine squared t can never be negative. So I don't need it, but I'll leave it. That's it. Wow, that took a while. You get the idea? Your question?
I was just seeing how you would check that.
Oh yeah, how would you check that?
Because I want to see what happens with the negative.
Okay, let's do it. So if I were going to take the derivative of this to check it, the negative will come for the ride, right?
Yeah.
Times, now, derivative natural log of something is 1 over it, times chain rule derivative what's inside. Derivative of 1 is 0, plus derivative of this is chain rule. So here's 2, right? Times cosine t times derivative of cosine t is your negative sine t, right? And there's your negative and your negative, which is going to turn it back into a positive. So if we put all that back together, we get the original integrand. It works. One more. And this one I'm showing you because it's interesting. Now, in a Cal 2 class, when you get to the section substitution, you'll spend at least 1 day on it. I can't, it depends on the instructor, but usually about 1 day, maybe 1.5 days on substitution. And then at that point, you have to make sure you understand it, and then you move on to the next idea. At least you're getting a preview of it here, so that way, that always helps when you've seen it twice, right? All right, so if, again, we're looking at this, we're saying this is in the substitution section, so it should work out with the substitution. Then I start thinking, do I see something in its derivative? X minus 3? What's its derivative? 1, and you see its derivative there? Yeah, there's a 1 next to this, right? I mean, there's a 1 right here, right? Agree? So we could try that. Now, let me give you a warning here. Whenever you're doing substitution, never make the substitution u is equal to x by itself. And here's why. If I do this, and I take the derivative on both sides, I get this, right? And then if I bring the dx on both sides, this is what I have, right? Now let's rewrite the problem. That integral will become, well, what's x? What's x? U, okay, parentheses, what's x? U minus 3 to the 400th. What's dx? du. Congratulations. What have you done? You've rewritten the problem, but now you've changed from x to u. But it doesn't help you at all. So never make the substitution u is equal to x, because all you're doing is wasting your time. Now x minus 3, maybe that will work. I don't know. Let's see. Why is the what?
Why would you not get like part of the x minus 3?
Or did I not grab enough?
Okay, yeah. All right, so let's talk about that. You said x minus 3, right?
Did I grab enough though?
Did you grab enough? We'll see. Let's first address this question. Why not grab the x minus 3 to the 400? The derivative of that would be what? 400 x minus 3 to the 399, right? Yes? So this whole thing right here, right, is the u, which means what's left over needs to be the derivative of it, right? And it's not, because what's the derivative? X minus 3 to 399. I don't see that here, right? You got to be able to see it there. Got it? If you're calling this your something, then you can hide it. Is what's left, the derivative, is that there? It's not. So that was taking too much.
So you can take pieces.
You can take smaller portions, yes. So x minus 3 was the other candidate. Let's try that. Just x minus 3. What's the derivative of x minus 3? 1. Just 1. And then let's do the dx on both sides. We get du equals dx. And this doesn't look very promising at first. It doesn't. But something really nice is about to happen. What am I going to replace x minus 3 with? U. So this piece right here is going to be replaced with u. And then what am I going to replace dx with? Du. So these two pieces are taken care of, aren't they? So I've got like u to the 400th power. I've got dx can become du, but I still need to figure out what I'm going to do with the x. And you can't have x's and u's mixed up together. It's got to be all x's or all u's, not both at the same time. So any idea what I can do with x?
You can put du there.
Du is dx, not x though, right?
Why? Because
Yeah, look at this equation right here. That's an equation that you created, right? That we created. We said u is x minus 3.
U minus 3.
So, close.
Or U plus 3.
Just add 3 to both sides of this equation, right? And you get that x is u plus 3. Right? So I can replace x with u plus 3. And again, that may not look like it's going to make life easier, but it is going to make life a lot easier. Does everyone see what I just did, though? Okay, let's rewrite this. This new integral becomes, the x is what? U plus 3. I need to put that in parentheses because it's two terms. U plus 3. And this ugly thing that was raised to the 400th power, that's now just u to the 400th, isn't it? And then du. Why is this better than the original problem? Well, this one was all x's. Why is this better?
As you said so.
Because the power is now just u.
That's right. Check this out. Look at this right here. The reason why this was such a pain in the butt was because if I wanted to, I could actually take x minus 3 and multiply it times itself 400 times, right? Multiply that all out. It'd take me probably about 6 months, but I would do it, right? I'd multiply it all out, make sure all my coefficients were right, and once I figured out what that was, I could pass an x through to all of them, and then I could integrate each one just using the power rule. Couldn't I? Because they would all be powers of x. That's no way, there's no way I want to do that, right? But when we converted it to an integral with u instead, look, u to the 400th is no longer a binomial being raised to the 400th power. It's just u, isn't it? And now what I can do is just pass this right through this parenthesis. And this just becomes integral u to what? 401 plus 3 u to the 400 du. Did y'all see that? I cannot do that here, right? Order of operations does not allow me to pass this x through because order of operations tells me I have to do the exponent before I do multiplication. Here, u to the 400 is u to the 400th. So I can pass it through. And now to integrate this, I can do each one separately using the power rule. So what is the antiderivative of u to the 401? What is it? 1 over 402, u to the 402, then plus antiderivative of this one. 3's coming for the ride. 3 over 401. Right? I'm adding 1 to this power. 3 over 401 u to the 401 plus some constant. And then my final answer, I have to go back and replace all my u's with x minus 3. So the final result would be 1 over 402 x minus 3 to the 402 plus 3 over 401 times x minus 3 to the 401 plus c. And that's it. That's the antiderivative. It's kind of cool, right? Kind of interesting. That substitution doesn't look at that it's going to work or help, but it actually does exactly what we need it to do. So that's why I say you have to try and you have to fail and be ready to get back up and try something again. I think this one is worth a quick check. Let's do a quick check. I don't believe that the derivative of this is that. Do you? All right, so let's do the derivative of this. The 402 pops out. 402, that's just a 1. So that would be x minus 3 to what power? 401. Okay, plus, now the 401 pops out here. And I get, what, just 3 and then x minus 3 to the 400. By the way, I did the chain rule. I don't know if you noticed that. The 402 came out. It was all this to the 401. And then I did derivative of inside also, which was 1. I just didn't show it, right? Same thing here. Is that that? Yes. Look at, they have a common factor. Don't they both have an x minus 3 to the 400th power? Don't they both have that? And so I can pull that out. If I pull it out of here, what's still here? X minus 3, one factor, right? X minus 3. And then what's left when I pull it out of here? Just the 3 plus 3. And these 3's cancel. And you get x times that. And no, there's no dx. Remember, the dx is really like a 1. It just helps us keep track of things when we integrate. So it's the same. Interesting. All right. You want this one? I erased it too already? Sorry. It was plus 3 over 401, parentheses x minus 3 to the 401 plus c. So I plan on giving you something on the test, on the final with substitution in it. All right. What do y'all think? Do you think you feel like you could do it, or do you feel like you're already saying no? I don't want to give you what the substitution is, but I'll make you a deal on the final. Is that if you can't figure out what the substitution is, you can come up and ask me, and I'll tell you what it is, but it'll cost you a point. A point on that problem. So if the problem's worth 10 points, then it's going to cost you a point. That's up to you. Okay? What's a bonus? No, substitution's on there. Look, I'm not giving you the full-blown substitution. I'm giving you the introduction to substitution.
It's not going to be like, I don't know, some of like the other problems.
Yeah, no, some of these get pretty nasty. Like the ones I just gave you right here are, to me, considered more on the nasty side. What I gave you in the previous class, where it was like x to the 4th and the derivative was sitting out there, 4x cubed, like glaring at you, that's more of what I'm talking about.
Because, I mean, you gave us some pretty nasty ones. Not today. But.
All right, we're going to move on. Evaluation theorem. This will be the last thing we do.
Is this on the test?
Yep, but you're going to like it. No, I promise you're going to like it. I promise you're going to like it. But it's going to take me a little while to develop it, all right? So you're just going to have to hang tight. Everything I do right now is just developing the idea, making you believe we can do what we're about to do, and then I'm going to show you an example. Once I get to the example, that's where you really need to make sure you're like locked in, all right? So for right now, just pay more attention to what I'm doing and kind of like yes, no, as opposed to just copying everything I'm doing down. All right, I'm going to remind you, recall what we called MVT, which was the mean value theorem. This was in chapter 4, and we had skipped it. I don't know if you remember. We did these things, and I said, we're going to come back to this because it's kind of on its own. And so I want to just remind you what it said. It said, if f is continuous on a closed interval, and f is differentiable on the interior of that interval, then there exists why does that not look at all right? Does that look right to you? No. Why can't I spell exists right now?
ISDS.
I-S.
ISDS.
I was putting too many, why was I putting too many S's in there? All right, exists. There exists. That's why we do this in math. so we don't have to spell. That's the sign for there exists. Then there exists a C in a B such that f prime of C equals f of B minus f of A over B minus A. All right. Maybe this rings a bell, maybe it doesn't. I'm going to draw the picture that goes with this quickly. We have a function. It's defined on a closed interval. Here it is f. Here's A. Here's B. This theorem says that if you take the slope of the secant line, that's this. It's the difference between the y values divided by the difference between the x values. That gives you the slope of this line. Okay, that's this red thing. The slope of that line has to be equal to the derivative somewhere. So somewhere in here, I should have a tangent line that is parallel. Okay? That look familiar? All right. That's what this theorem says. I want you to notice some things on this. A and B are the left endpoint and right endpoint of this interval, right? A is the left endpoint, B is the right endpoint. I want you to also recognize that C is guaranteed to be in here, and it's in between A and B, right? It's guaranteed that it's inside A and B, not including the brackets. And that's it. That's all I want you to make sure you understand. Left and right endpoint, C is in the middle. Now I'm going to take this equation, and I'm just going to do something to it real quick. I'm going to multiply both sides by B minus A. Multiply this by B minus A. And do you agree if I do that, it will cancel over here, and I get this, which I'm going to have to put right up in this corner for me, because I'm going to need it. I'm going to write it f prime of C times B minus A equals f of B minus f of A. Is that okay? That's just me taking that formula, which is guaranteed to always be correct through the mean value theorem. And then below that, I'm going to write one more thing, and I'm going to ask you what I did. All right? So below that, I'm going to write this. So do you know how when we were doing integration, we always said that capital F is the antiderivative of little f? Right? Capital F's the antiderivative, which means little f is the derivative of capital F. I'm saying it this way. The derivative of capital F is little f, because the integral of little f is capital F. That's the relationship between capital and lowercase f. So right here, what I'm doing is I'm using the same formula, but instead of using little f here, I'm using capital F, right? Instead of little f here, I'm using capital F. And this f right here is the derivative of that, right? And what is the derivative of this one? Of capital F? Little f, right? So do you see that this is the same formula, just written with different letters? Yes? You sure? This little f is the derivative. This is the derivative of little f, so it's the derivative of that function. Little f here is the derivative of this function, which is capital F. It's the same exact formula, but I'm using a different... Instead of calling this function little f, I'm calling it capital F. And then instead of writing capital F prime here, of C, what is the derivative of capital F? Little f. Okay? So scrap this. All right. Now I'm ready to get to the evaluation theorem. Well, Still building up to it, all right? Our goal here is to try and find the area underneath a curve. What's that area? That's our goal. Now, let me try and motivate this a little bit. If you look at the history of human thinking, all right, very early on, we were able to determine areas of very common shapes. First, a rectangle. We are all very comfortable with the area of a rectangle, length times width, or if you want to say width times height, doesn't matter. It's this side times this side, right? Area of a rectangle. And if we do something more complicated, like maybe some weird shaped polygon like this, we can find the area of that. And the way we could do it is we could come in here and start cutting this thing up into triangles, and then we could find the area of all the different triangles, couldn't we? Area of triangles, 1/2 base times height. So we could work it out. This would take a lot more effort than it would here, right? But that could be done. So if you look at the history of things, it was really the motivation of people like taking land and saying, this land's mine, right? This is my property, that's your property, here are our property lines. How much property do I have? What's the area of my property versus yours? Well, property lines are not always straight. Maybe your property runs up against a river or something like that. So it's pretty natural to say, well, can we find the area of just an arbitrary shape where you have curves in the shape? Understand? There's no like general formula for this. Well, I don't know, can we? I think this would be a natural place to start. If you can find the area underneath this curve, right, then you're on your way to finding your area on weird shapes, because you're able to handle the curve now and still get an area. Make sense? And the most basic example of this is something that the Chinese went after a long, long time ago. They went after this problem. You know, you sit there and you nail a stake into the ground, and you take a rope and you start walking around, and you come back, you're going to draw a circle, right? So if you draw a circle and you know what its radius is, what's the area of it? Pi r squared. Yeah, but before, where did that come from, right? Was that like on the back of some tablet? I like to joke about that, but I better not. We've become so damn politically correct. I used to make a joke about, you know, the 10 Commandments. I guess I'm going to make the joke. Anyways, so look, imagine you don't have pi r squared, right? You don't have that formula. So what's the area? Well, the way the Chinese did it is they used what's called the method of exhaustion. Like, yes, you're exhausted. What they did is this. They said, okay, well, what we do know is we can draw some pretty good rectangles. We're pretty good at drawing rectangles. They get like very, very straight edges, and they would use very, very precise pencils, and they would draw these rectangles, and they would measure the lengths and heights and widths of all these little rectangles, and they would add them up. And they would draw even smaller ones in all these little corners. And do you see that there's going to be error? E-R-R-O-R. There's going to be error. There's going to be spots where they just don't quite pick up that area. Do you know what I mean? So they add up all these red rectangles. They get a total sum of all the rectangles. They call that the area. And I'm going to put L for that's too low, right? That's actually less than the true area. And then they would they'd be kind of clever, and they'd say, all right, well, what about if I draw a square around that? Do I know the area of that square? That's more than the true area. It's bigger. So they would find the area of the square, then they would start drawing rectangles in here and start subtracting those from the area of the square. So you take the whole square, start taking out all those little rectangles in there, and add that up. That would be too much, wouldn't it? It would be an overestimate. So they would have a blue number, right? That would be too large. I'll just say O for overestimate, all right? This number's too big, this number's too small. The true area lies between those two. And they would just get better and better. They would exhaust themselves drawing rectangles and measuring until they squeeze that number down between two things. And they got pretty damn close. They were able to say that the area was approximately 22/7 r squared. 22 over 7 is an approximation of pi, but it's not right. It's not pi. And it's not the true area. We all know that's pi r squared, right? They couldn't come up with pi. They always had a little bit of error to it. 22 divided by 7. Let me see. I don't remember. 3.1428. Pi is like 3.1415 something. So it's off within the first 3 digits, 3 decimal places, it's off. But for most applications, in that time, in that day and age, that was good enough, all right? Then Newton came along and said, no, we need to figure this out. We need to figure out a way of doing this. So you know that all of calculus is based on the idea of the limit, right? I've said this from the beginning. It's all based on the idea of a limit. So if I were to try and get this A and squeeze it down to a single number, what I would need to do is let the number of red rectangles go to infinity. The more I draw, the better my estimate is, right? And the more blue ones I draw, the better this estimate is, and I'm going to squeeze it down. And I'm never going to stop. I'm going to say, no, I'm not going to put 100 rectangles in here. I'm not going to put 1,000 in there. I'm not going to put 10,000. I'm going to put an infinite number of rectangles in there, which really doesn't make a lot of sense until calculus comes along. Then the idea of letting something go to infinity and getting an answer does make sense. You kind of follow the idea there? We're about to use that same idea right here, right there. I'm giving you a preview into Cal 2 right now, all right? So I'm just erasing the formula I'm going to need. All right. Here we go. Here's how I'm going to do this. I'm going to take that function again, and I'm going to try and find the area below this. And so here's one possible concept. I know the area of rectangles. I'm really good at that. I can handle that, length times width or whatever I can do. So what if I first take A and B here, and why don't I cut this line segment between A and B, why don't I cut it up into equal pieces? Now, how many of them I cut it into? That's up to me. So I'm going to cut them into n pieces.